Hello class, welcome to the chemistry of radicals. As the name suggests, a radical is an atom that has an unpaired electron. If the atom has two unpaired electrons, then it becomes a diradical. But in this case, we're looking about an atom with an unpaired electron. Now, how is a radical formed? Free radicals are formed when a bond breaks homolytically. As you can see here, we use fish hooks to signify a homolytic cleavage of the bond. As you can see here, the bond breaks homolytically. So we are using fish hook. This is a fish hook. The fish hook signifies that each atom goes away with one electron. Remember, a bond is made up of two electrons, so when the bond breaks, the atom goes away with one electron. And these kinds of reactions are usually promoted by the presence of light and heat. So the formation of free radicals is promoted by the presence of light and heat. And so let us make this distinction right from the start. A double barbed arrow, as you can see here, signifies a heterolytic cleavage, while a single barbed arrow or a fish hook signifies a homolytic cleavage. And don't forget that the double barbed arrow shows the movement of two electrons, while the single barbed arrow or the fish hook indicates the motion of one electron. As you can see here, this is a heterolytic cleavage. Because you can see that the carbon bromine bond breaks in a heterolytic fashion, with bromine taking all the two electrons, leaving carbon with no electron. That gives carbon a formal charge of positive, while the bromide has a formal charge of negative. It's positive in the sense that it has one less valence electrons, while the bromide means it has one more valence electron. Now recall that the orbital hybridization in carbocations and carbanions. Remember, a carbocation has an empty unhybridized p orbital, and that empty unhybridized p orbital can accept electron density. And because of that, because it only has 3 electronic regions, it is sp2 hybridized. On the other hand, the carbanion has 4 electronic regions, and as a result, it is sp3 hybridized. As you can see here, because of that, it's going to have a trigonal pyramidal geometry, molecular geometry, while the carbocation will have a trigonal planar geometry. Now, free radicals are thought to actually be sp2 hybridized or quickly interconverting to sp3 hybridized atoms. Okay, but we expect, because it has 4 electronic regions, it has 1, it has 2, it has 3, and it has 4 electronic regions. Even though we expect the atom to be sp3 hybridized, experimental evidence suggests that it's sp2 hybridized. So the actual geometry will be trigonal planar. So in an exam, you want to state that the geometry of a radical is trigonal planar rather than trigonal pyramidal. We expect it to be trigonal pyramidal. That's what we expect, because it has 4 electronic regions. But we have to go with experimental evidence, because chemistry is a science. In a science, you need to make observations, and this is the observation points to the fact that it's actually trigonal planar and sp2 hybridized. Now, free radical stability. Free radicals do not have a formal charge, right? They don't have a formal charge because the number of valence electrons is equal to the number of electrons present, right? However, they are unstable because they have an incomplete octet. They don't fulfill the octet rule, and so they are unstable. Now, groups that can push or donate electron density towards the free radical will help to stabilize it, okay? And we know that happens just like in carbocations. through the phenomenon known as hyperconjugation. That's the phenomenon known as hyperconjugation. And typically what really happens is electron donation through space. Okay, typically from the bonding molecular orbital to the anti-bonding molecular orbital. So hyperconjugation is electron donation through space, typically from a bonding molecular orbital to an empty anti-bonding molecular orbital. Remember, we talked about molecular orbitals and anti-bonding molecular orbitals when we're looking at the molecular orbital theory. Okay, now the same trend that we observe in carbocations is the same trend that is observed with radicals in terms of stability. Just like in carbocations, we know that the tertiary is the most stable. Following that is the secondary radical, while the primary and the middle is the least stable. And the reason again is due to hyperconjugation. So let's make a note of it. And because of the stability of the tertiary radical, the bond dissociation energy is going to be the least. As you can see here, the bond dissociation energy is the least. And that's because the product is more stable. The product is more stable, so the bond is going to break easily. Okay, as opposed to that of a methyl radical. You can see the bond dissociation energy is very, very high. That's because the radical that forms is very unstable, and so the energy that is required to form this intermediate is going to be the energy to form this intermediate is going to be very high. As you can see here, look at my little diagram here. You can see that for the methyl radical, look at the methyl radical, the activation energy, the energy required to go from methane to the methyl radical, okay, is going to be very, very high. It's going to be very, very large. You see, it's going to be very, very large, because if you follow this blue line, here, right, and look at where you can see that right here, the energy is going to be the largest. You see, and the reason is because of the fact that the methyl radical is unstable. See, it's more stable. As you look at my little example here, if you consider, say, a tertiary carbon that is connected to three other carbons, right, the breaking of the bond is going to be product favored, because it forms a more stable radical. The equilibrium will favor the product side because this is more stable. This is more stable, right? If you have more stable products, of course, the equilibrium is going to favor the more stable, the more stable products, and not the less stable products. We learned that, okay? And that is why you can see, because of the significant stability of the tertiary radical, the bond dissociation energy is really, really much smaller than the bond dissociation energy of the metal. The breaking of the carbon hydrogen bond being broken to from the metal radical. Now, so you can see that relative stability of radicals is evidenced in the bond dissociation energy. Okay, the more stable the radical that forms, the lower the bond dissociation energy. The less stable the radical that forms, the higher the bond dissociation energy. And basically that's how it goes. Now, so if we have to draw resonance for free radicals using fish hook, we use fish hook arrows to show electron movement. Don't forget that for radicals. Okay, remember, for resonance, the arrows don't actually show electron movement. All we are trying to do with resonance is showing the delocalization or distribution of electron density. See, we're not really showing electron. Basically, what we're trying to do is using multiple Lewis structures to show the actual structure of the molecule. Okay, and that way we'll be able to see the way electron density is distributed over the molecule. So if you have to draw the resonance hybrid for the radical here, you can see what is happening. You can see you use fish hooks. Okay, and if you want to go backwards, basically what you need to do is go like this, go like that, and this dumps there like that, and this will be the hybrid that forms. This is the hybrid. Now, how does resonance affect the stability of the free radical? Remember that resonance increases the stability of the radical through delocalization of electrons. Remember, we learned in Chem12B that a localized charge is more stable than a localized charge is less stable, I beg your pardon, is less stable than a delocalized charge. A delocalized charge is more stable, right? Because it's spread all over the molecule. Okay, and that's the advantage of resonance. This resonance helps the molecule to achieve greater stability by the delocalization of the charge. Now, if you look at benzylic radicals, you can see that it's benzylic in the sense that this is an allylic carbon to the pi bond. You see, if it was just this would be allylic, but because it's a benzyl group, that's why we call it benzylic. See, and look at how the electrons move again. All right, look at how the electrons move. So this is something that you have to get used to. You see, you have to get used to it. Okay, because we're going to be doing several examples. Now, let me just do one quick help you do this example here. If you look at here, you have, by the time you have everything delocalized, what's going to happen is you're going to have the electron here, okay, like that. And then by have this time delocalized, you're going to have this electron here, like so. And by the time you have this delocalized, you will have arrived at what you started with. You see? And so if I'm going to draw the resonance forms here, all I need to do is go like this and go like this. I'm sorry, not that way. I need to go. So basically, what you have to do is to get this one is you go like this, and you go like this, and you go like this, right? And then to get to this one where you started with, all you need to do is go like this, you go like this, and go like this. See that? So you see, we are using fish hooks. We're using fish hooks. You see, that's what we're using to be able to show the distribution of electrons. And by the time you draw the hybrid, you can see that the electron density is located at all these carbons here. See, that's where all these carbons, and that's why they have a partial charge. Okay, now how does resonance affect the stability of a radical? You see, resonance increases the stability of the radical through delocalization of electrons. You see, through delocalization of electrons. So you have tertiary, you have allylic, you have benzylic. Okay, what is the bigger factor here? Hyperconjugation, right? It's actually hyperconjugation and resonance that is happening, but the bigger factor here is resonance. You can see that the charge, the radical here, is going to be stabilized by resonance. By the time this loses the hydrogen, it's going to be benzylic in nature, and it's going to be stabilized by resonance. Similarly, by the time this loses its hydrogen, when you have the breaking of that carbon-hydrogen bond, you're going to form a radical that is resonance stabilized. So the big factor here is resonance. And that's why you can see that there's a significant decrease in the bond dissociation energy, because you are forming a more stable radical, and as a result, the bond dissociation energy is going to be much smaller. Vinylic radicals are especially unstable. We know that, right? They're especially unstable. So vinylic radicals are especially unstable, and the reason is because, you see, when this bond breaks, it cannot be stabilized by resonance. It cannot. Why? Because it's in an sp2 hybrid orbital, and this is in a p orbital. These are perpendicular, so you can never have delocalization of electron density. So that's very unstable, and that is why you have a very large bond dissociation energy. It's a stronger bond, like I'm trying to explain here. It's a stronger bond because the vinylic radical cannot be resonance stabilized. It cannot be resonance stabilized, right? While this is a weaker bond because the allylic radical is resonance stabilized. And that is why it's a weaker bond. So what type of